In the final years of the conflict, the Third Reich shifted its efforts away from the front. In hidden tunnels, underground facilities, and forested areas, groups of engineers and technicians began developing weapons unlike anything seen before. The objective was no longer to improve troops or vehicles, but to create tools capable of immediately destroying the enemy. Many of the plans remained on paper due to their size, cost, or technical unfeasibility. Some were tested, but did not offer decisive results. The documents recovered at the end of the war showed the extent to which they tried to manufacture devices capable of causing massive damage without warning. What were the secrets of those weapons that wanted to annihilate millions but failed in the attempt? Vogle, the aircraft that planned to bomb from orbit. The Vogle project emerged as a German attempt to develop a space bomber during the Second World War. Its design proposed the use of a booster ramp that would allow it to reach hypersonic speeds, with the aim of launching bombs on distant targets. The vehicle was conceived to take off with the aid of an inclined rail and an additional rocket system that would provide the initial thrust. After leaving the ramp, the apparatus was supposed to continue ascending up to 150 kilometers of altitude, with an initial acceleration of up to 20 times the gravity. In that trajectory, it would enter a partial orbit that would allow it to glide long distances, skimming the Earth's atmosphere. The original design specified a trajectory with successive bounces over the upper layers of the air, which prolonged its potential range without the need for continuous propulsion. The body of the craft had a length close to 28 meters and a wingspan of 15 meters. Its total weight at launch would reach 100 tons, while empty it would weigh about 9. The initial thrust of the main engine would be 610 tons for 11 seconds. The dimensions and characteristics of the engine were intended to take the vehicle to an approximate speed of Mach 10. The Vogle vehicle was designed with a very demanding aerodynamic and thermal load. Upon reaching suborbital altitudes and extreme speeds, the skin of the apparatus would be subjected to temperatures exceeding 1,300 degrees Kelvin. To withstand these conditions, the design foresaw the use of materials capable of resisting high temperatures without compromising the structure. The blueprints proposed that the apparatus would release its explosive payload over the target after a trajectory correction phase, called the third direction phase, just before the release point. Then, the vehicle would follow its descending trajectory and land on a pre-established runway after having traveled thousands of kilometers. The main engine, classified as a 10, had a loaded mass of almost 70 tons, while its empty structure weighed just under 17. Its height was 20 meters, and its diameter was slightly more than 4. This engine offered a thrust exceeding 2 million newtons, with a specific impulse of 247 seconds, reduced to 210 at sea level. The estimated duration of combustion was 55 seconds. The upper module, designated A9, had a total mass of more than 16 tons and a structural mass of 3. It measured slightly over 14 meters high, with a diameter of 1.5 meters and a wingspan of slightly more than 3 meters. Its thrust was almost 300 kilonewtons, with a combustion duration of 115 seconds. Its maximum altitude would reach 200 kilometers, and its flight range would be 1,000 kilometers. In one of the design schemes, the apparatus was projected to ascend rapidly to 3 kilometers at Mach 1.5 speed, and then continue climbing for about 8 minutes until reaching its suborbital ceiling. From that position, it would perform an intercontinental flight with atmospheric skipping before releasing its payload. One of the documents that mentions this project is a research study by the German Luftfahrtforschung, where a rocket propulsion system for long-range bombers is analyzed. The report details the vehicle's architecture, its navigation system, and the re-entry parameters. The planned guidance system included instruments capable of maintaining the orbital trajectory without significant deviations and relied on mechanical and gyroscopic mechanisms. Aerodynamic control was achieved thanks to movable surfaces installed at the rear of the apparatus, which allowed for precise course adjustment during the phases when it flew within the atmosphere. When comparing the Vogle to space vehicles developed later, such as the American Space Shuttle, it was clear that it had an advantage. Its lift-to-drag ratio reached a value of 5, while the North American model barely reached 4.5. This difference reflected greater efficiency and prolonged gliding. After the war, the knowledge accumulated in this project sparked the interest of several powers. Attempts were made to recruit the design leaders, including Eugen Sänger and his collaborator Irene Sänger-Brett. The technical documents on the Silbervogel were studied in detail by both the United States and the Soviet Union, who sought to leverage the German experience in advanced space technologies. In a later stage, Sänger developed theories on photonic propulsion as an evolution of the initial Silbervogel concepts. These ideas considered the use of light-based reaction energy, capable of achieving relativistic speeds with very small masses. Although these proposals were not directly connected to the Silbervogel, they shared the objective of creating transport systems that would surpass the known atmospheric limits. The final design phase included estimations of the thermal effects of the flight, the power generation during the initial impulse, and the vehicle's capacity to withstand the stress of multiple atmospheric skips. In particular, it was calculated that the external surface would experience extremely high dynamic pressure during re-entry. The Silbervogel was never built, but the associated studies marked a technical precedent that would influence the subsequent development of missiles, orbital vehicles, and advanced propulsion theories. The concept of suborbital flight combined with atmospheric skipping was revisited decades later in American and Soviet aerospace proposals, albeit with very different technologies. Sonengewehr, the space mirror that targeted Earth. The regime chose Hillersleben, a locality surrounded by hills and dense vegetation, to erect its main weapons testing site. There, a group of more than 150 specialists in physics and engineering tested dozens of prototypes, several of which were used during the clashes. When the Allies took control of Germany in May of '45, the complex was left behind. In the abandoned facilities, they discovered weaponry in different phases of preparation. There were rocket launchers, armored vehicles adapted to fire at long range, 600mm cannons, and many other pieces that were about to be implemented. Among all the documents found, a design attributed to Hermann Oberth stood out, who would later be considered a key figure in the development of space technology. The project, known as Sonengewehr or solar weapon, proposed a structure located in near-Earth space. According to the papers found, the station would be assembled in parts built on the surface and then transported off the planet. The procedure was similar to the one that would be used decades later for the International Space Station. There was even a description of how to generate artificial gravitational force from a constant rotational movement. Among Oberth's proposals, the one that most attracted the regime's high command was the creation of a concave reflector with an approximate diameter of 3,000 meters, capable of redirecting concentrated sunlight toward a specific point on Earth. It was an idea that vaguely recalled a principle attributed to Archimedes, where rays were used to burn rival ships centuries ago. The German technicians, based on Oberth's calculations, concluded that the ideal location for the mirror would be about 8,200 kilometers in altitude. The compound chosen for the reflective surface would be metallic sodium, a material that effectively reflects light and is common in the natural environment. Although sodium reacts violently upon contact with water, this detail did not generate inconvenience, as there is no moisture in the vacuum of space to alter its properties. The different sections of the mirror would be placed into orbit using an evolution of the V-2 missile. This new version, named V-11, was designed by Wernher von Braun. The artifact would have the capacity to send people off the planet and, at the same time, would be used as an intercontinental attack vector, with the possibility of impacting North American soil, just as the V-2 had done over British territory. The devised system also included internal spaces intended to house the crew members. Some parts of the project may seem naive from a current perspective, but in that period, knowledge about space conditions was minimal. The electrical supply would be generated by means of devices similar to dynamos, which would function thanks to solar radiation. Operators would wear shoes with magnets to walk on the interior surfaces without floating, and breathable air would be obtained through crops. A controlled pumpkin plantation would absorb the carbon dioxide released by the crew and continuously release oxygen. The orders would be sent from the ground base using coded signals. Once received, the team in orbit would use a control system to orient the mirror toward a point on the planet. There was no risk of direct attack against the structure, since at that time no force had the means to destroy it from the ground. With the entry of the Allied forces into German territory, all preparations were abandoned. It is probable that, even if it had been built, the projected light concentration would disperse upon entering the atmosphere, reducing its effect to a simple flash on the horizon. Several experts involved in this scheme, including Oberth and von Braun, were later taken to the United States. There they continued with their developments in space propulsion. Paradoxically, the same technology that had been used to raise cities like London later became the basis of the Saturn V vehicle, which made possible the landing of the Apollo program astronauts. Ju-390, the aircraft that skimmed the coast of the United States. The Ju-390 was a modification of earlier models, expanded by sections added to the wings and fuselage. Its first prototype completed its initial flight in October of 1943 with positive results. Following this success, the Air Ministry requested the production of 26 units under the designation Ju-390A1. Manufacturing did not advance, as the program was cancelled along with that of the Ju-290 around mid-1944. Versions intended for maritime patrol and bombing were also planned. The surveillance model was named Ju-390B, while the bomber was designated Ju-390C. This latter version, in theory, could carry a small Me-328 fighter as embarked defense. There are records of tests with the Ju-390 carrying an anti-ship guided bomb of the Fritz X type. Of the two prototypes built, the first received the code GH+UK and was associated with the FAGR-5 unit. Some testimonies indicate that the second one also flew. The test pilot Eiserman documented a flight in February of 1944 aboard that aircraft, although its fuselage was never found. Surviving photographs of both models in the air support the hypothesis that both were operational in the testing phase. One of the most commented uses was a supposed long-range flight to Japan. Albert Speer, Minister of Armaments of the Third Reich, claimed in a later testimony that a Junkers crew made a polar crossing to Japanese territory in 1944. That operation, if it occurred, was not supported by technical documentation, but by personal memoirs. Regarding its technical design, the Ju-390F1 had a crew of 10 people. Its length was 34 meters, with a wingspan of more than 55 meters and almost 7 meters of height. The total wing surface area reached 254 square meters. Empty, the aircraft weighed 39.5 tons, and with full load could exceed 75 tons. It had 6 BMW 801D radial engines, each with 14 cylinders and a power output exceeding 1,200 kilowatts. In terms of performance, this prototype reached a maximum speed of 505 kilometers per hour. It had an estimated combat range of 9,700 kilometers and an operating ceiling of 6,000 meters. Its wing loading was 209 kilograms per square meter, and the power-to-weight ratio remained at 0.17. The defensive armament consisted of 2 MG 131 13mm machine guns on the sides, 2 of the same type in the bow gondola, 1 MG 151/2020mm cannon in the tail, and 2 other identical cannons distributed in dorsal turrets. Furthermore, the plane included a Fuji 200 Hohentwiel radar for navigation and detection. The Ju-390 never advanced beyond the development phase. Despite the intentions of converting it into a long-range bomber, oceanic patrol aircraft or strategic transport, no unit was mass-produced. Its history remained limited to experimental tests, hypotheses of special flights, and scattered records. The project ended up archived along with other designs that sought to expand the air capacity of the Third Reich without achieving effective implementation. The America bomber proposal, of which the Ju-390 was a part, was finally discarded. It competed with models like the Me-264 and the TAR-400, all with the goal of reaching North America non-stop. Although technically feasible, logistics and the war context prevented them from going beyond the planning boards. The Ju-390, like its competitors, was reduced to images, blueprints and isolated testimonies that kept it alive as one of the giants that never got to fight. Fliegerfaust, the rocket launcher that failed on the air front. The Fliegerfaust project, also known as Luftfaust, was a German initiative to create a portable rocket launcher designed to shoot down enemy aircraft from the ground. It was developed in the final stage of the conflict, when Allied air superiority was becoming increasingly overwhelming. It was conceived by the firm HASAG, located in Leipzig in the year 1944. The initial design led to 2 distinct versions that sought to increase the weapon's range and accuracy without losing portability. The first variant, called Fliegerfaust A, had 4 launch tubes. Each launched a 20mm projectile weighing 90 grams, loaded with 19 grams of explosive. Although the design was functional, it was considered insufficient against the speed and altitude of enemy aircraft. Immediately after, the Fliegerfaust B, also known as Luftfaust, was developed. This version incorporated 5 additional barrels, reaching a total of 9. The weapon measured 1.5 meters and weighed 6.5 kilos. Its firing mechanism was divided into 2 stages. 4 rockets were launched first, and 1/10 of a second later, the remaining 5. This prevented collisions between projectiles and maintained trajectory stability. In addition, an experimental prototype named Fliegerfaust C existed. This model mounted 6 30mm tubes and used ammunition from the Mk-108 automatic cannon, common in aircraft like the Me-262. Each projectile weighed 330 grams and carried 75 grams of explosive. However, this prototype never passed the testing phase. Regarding its actual use, the Fliegerfaust demonstrated significant limitations from the start. Although it theoretically should have reached targets at 500 meters, the dispersion of the rockets drastically reduced its effectiveness. As a result, the weapon did not meet expectations. Even so, in 1945, massive orders were placed. More than 10,000 launcher units and nearly 4 million rockets were requested, but only a small fraction was completed. According to records, only 80 devices were used experimentally by a unit stationed in Saarbrücken. When American forces took Leipzig, they found the HASAG facilities intact. Inside, thousands of unused Fliegerfaust were stored, which were sent to the United States for analysis. Subsequently, the studies carried out on this model would serve as the basis for the future portable anti-aircraft systems used by that country. V3, the supercannon buried in the hill of Mimoyex. In 1943, Saar-Röchling presented an unusual design. It was a 140-meter cannon, intended to attack at long range without the need for guided projectiles. The weapon, known as V3, used the principle of multiple angled side charges that ignited sequentially. The idea was not new. Decades earlier, Lyman and Haskell had tried it unsuccessfully, as the flames from the base charge reached the subsequent chambers before the projectile passed. The engineer Condors proposed a solution in 1941. Activate each charge with electrical pulses, synchronized with the projectile's movement. That same year, a reduced model of 20mm caliber was built at a test site in Mystroy, Poland. During the spring trials of 1943, the weapon worked as expected. Hitler, upon learning the results, decided to advance the project without consulting the High Command. He wanted a third retaliation weapon after the V1 and the V2. The proposal was to build a battery of 50 cannons pointing at London from a point near Calais. Thus was born Operation Vise, which contemplated the construction of 5 tubes mounted inside a chalk hill. Each tube would be installed at a fixed angle, covered by a concrete vault more than 5 meters thick. The projectile, weighing 140 kilograms, was supposed to travel the 140 meters of the cannon with the help of the ignition chambers, placed every 3.5 meters. Thanks to the progressive ignition, the velocity upon leaving the tube would exceed 1,500 meters per second. No rifling or internal stabilizers were used. The projectiles were smoothbore with external fins, similar to the Canadian models that would emerge decades later. Construction began in September of 1943. Hundreds of forced laborers were used to excavate a deep tunnel into the Mimoyex chalk hill, located about 160 kilometers from London. From the start, the French resistance informed the Allies. In November of that same year, the first air attacks against the area began. Despite the continuous bombings, the structure resisted. Even the tallboy bombs of more than 5 tons did not cause relevant damage. But on July 6 of 1944, 3 of these managed to penetrate the access points to the shafts. They penetrated 30 meters until reaching the lower level. The explosion killed dozens of workers and paralyzed the progress of the work. The Allied command was unaware of the result of that attack. Because of this, they activated other plans. One of them was Operation Aphrodite. It consisted of converting B-17 or B-24 bombers into radio-controlled missiles. 2 pilots would take off with the aircraft loaded with 10 tons of explosives. Once airborne, they would parachute out, and another plane would guide the aircraft to the target. However, the tests proved catastrophic. The project was cancelled in August after several accidents, including the death of Joseph P. Kennedy Jr., brother of the future President of the United States. Shortly after, British troops advanced toward northern France. In late August, the Germans abandoned the Mimoyex complex without having put it into operation. None of the supercannons managed to fire against London. In December, an attempt was made to reuse the concept with reduced versions. 2 units of 45 meters in length were built in Antwerp and Luxembourg. The objective was to support the Battle of the Bulge offensive, but the performance was low. Barely a few shots were fired, and no significant damage was recorded. The V3 system, despite its original technical approach, ended up being unfeasible. The difficulties in producing it on a large scale, its high cost, and the exposure to air attacks prevented its operational advance. On May 9th of 1945, the Mimoyex installations were destroyed by British troops, definitively closing the structure. That weapon, conceived as a direct offensive against London, was buried in rubble without ever being fired. Although it was never used in combat, it served as an example of the type of extreme solutions that the regime was pushing during its final stage. The most extensive piece manufactured during the war was reduced to an inert project, a reflection of a strategy that prioritized spectacle over practical application. Die Glocke, the Third Reich's most secret experiment. During the Second World War, a rumor emerged of a hidden device among the Third Reich's most reserved projects. Known as Die Glocke, or the Bell, it was first mentioned by the Polish researcher Igor Witkowski, based on alleged secret transcripts from the interrogation of SS officer Jakob Sporenberg. Witkowski claimed that in 1997, a contact from the Polish Secret Service allowed him limited access to confidential documents related to experimental German weapons. He could neither make copies nor keep the originals, only take notes. Years later, this story gained wider circulation after being picked up by the British journalist Nick Cook, who included it in his work on advanced Nazi regime technologies. Cook described a metallic object with a shiny surface that rotated on its own axis and was attributed with extraordinary effects on everything surrounding it. Some went so far as to link it with anti-gravity phenomena or with a still unknown energy source. Others associated it with experiments related to occult practices and even with possible time travel. The legend was expanded by connecting it with Hans Kammler, a high-ranking SS officer, who supposedly negotiated handing the device over to the United States in exchange for immunity when the war was about to end. According to the accounts, the apparatus was allegedly built in an ultra-secret facility known as the Giant, situated near the border with Czechoslovakia. It is said that the tests took place in the vicinity of the Wenceslaus mine, inside an underground complex hidden among the mountains of Silesia. According to the descriptions gathered, Die Glocke measured between 3 and 5 meters high and had a diameter close to 3 meters. Its structure clearly resembled a large bell, made of a heavy metal and completely covered with insulating materials. As the reports accumulated, details about the alleged operation of the device emerged. It contained within it 2 rotating cylinders that were filled with a violet-colored liquid similar to mercury, which was given the code name Serum 525. This fluid was stored in lead-encapsulated and highly insulated containers. During the tests, substances such as thorium and beryllium peroxides were also used, materials that increased the dangerousness of the experiment. The artifact's effect on living organisms was described as lethal: tissues crystallized, blood separated, and plants decomposed into a viscous substance. During the initial trials, new operational restrictions were implemented on the perimeter of the testing area. Activations of the device required an isolation radius exceeding 200 meters, due to the physical and chemical effects detected in each experimental sequence. Control over access was so rigorous that even many within the regime's own technical units were unaware that the project was underway. One of the elements that reinforced the legend was the presence of a ruined structure known as the Henge, located a short distance from the mine. It is a concrete ring with vertical columns whose function was never fully clarified. Some researchers speculate that it may have been a testing platform for Die Glocke, while others interpret it as part of an industrial cooling tower unrelated to advanced technologies. As more authors investigated, new theories began to emerge. Joseph P. Farrell proposed in his books that Die Glocke was part of a research program on exotic propulsion, free energy, and space-time manipulation. Henry Stevens, for his part, identified the violet fluid as a compound of mercury iodide, or even red mercury, due to its unusual properties. Others suggested that the artifact worked as a kind of temporal lens, capable of projecting images of the past through a concave mirror installed on its upper part. This story was attributed to the scientist Otto Czerny, who supposedly shared said information in the decade of the 60s. With the collapse of the Third Reich, the final fate of Die Glocke became a mystery. Witkowski insinuated that it may have been transferred to South America, to one of the pro-Nazi enclaves that operated in the region during the post-war period. Cook, on the other hand, maintained that it was delivered to the Americans as part of the secret agreements promoted by Kammler. Another more daring hypothesis holds that Die Glocke is related to the Kecksburg UFO incident in 1965, in which a metallic, bell-shaped object with unknown inscriptions was allegedly recovered. This theory was later reproduced by television programs focused on conspiracies and hidden technology. There is also the possibility that the device never left the underground complex of Der Riese, remaining hidden among collapsed tunnels or buried under rubble. Although some testimonies from SS soldiers and technicians suggest that certain elements of the project survived, there is no conclusive physical evidence to support its existence. Nor have verifiable official documents been found that confirm the authenticity of the original transcripts mentioned by Witkowski. Despite the doubts, Die Glocke continues to attract the interest of researchers and enthusiasts of alternative theories. For some, it represents a symbol of how far the technological ambition of the Nazi regime could reach. For others, it is merely a myth born of the chaos and secrecy that enveloped the final years of the conflict. Over the decades, its story has been adapted, reinterpreted, and mixed with elements of science fiction, which further complicates separating speculation from reality. The ruins of Der Riese still stand, visited by the curious historians and conspiracy theorists. There, among tunnels excavated in rock, abandoned concrete structures, and remnants corroded by time, some believe that the most extraordinary secret of Nazi Germany still lies hidden. As long as no tangible evidence is found, Die Glocke will continue to float between myth and reality, as a warning of what happens when science and power intersect without limits. E-100, the colossal tank that never entered combat. Around 1942, Germany launched an ambitious initiative, the E vehicle series, conceived to replace previous models such as the Panzer III, the Panzer IV, and the heavier Panther and Tiger. The objective was to unify components between different armoured vehicles to facilitate production and maintenance in the midst of the war of attrition. Within this family, the most colossal of all emerged, the E-100, an experimental tank that came to weigh 140 tons. Although it was a purely technical project, its design integrated the combat lessons accumulated by the units on the front and sought to incorporate technological improvements against the limitations already observed in other models. Its development was entrusted to the firm Adler, which proposed an initial design with an estimated weight of 100 tons. However, the incorporation of a 50-ton turret designed by Krupp, the same one planned for the Maus, and the lengthening of the chassis to house it raised the total weight of the vehicle to 140 tons. Unlike the Maus, which had a more experimental design, the E-100 maintained a conventional configuration with the engine installed in the rear. Its side armour, like the tracks, could be disassembled to facilitate its transport by train, an essential detail given its size. Tests were carried out with the Maybach HL 230 engine, the same one as the Tiger II. Although it developed 700 horsepower, this engine proved insufficient to move such a structure with agility. Speeds of only 20 km per hour were reached on flat terrain. As an alternative, Maybach was working on a new supercharged model, the HL 232, which promised 1,200 horsepower, with an estimated consumption of 10 litres per kilometre and a theoretical autonomy of 120 kilometres thanks to its 1,200-litre tank. With this more powerful configuration, a maximum speed of 40 kilometres per hour on the road was expected. The planned armament included heavy options, a 150 or even 170mm cannon. However, the available turret proved to be too small to accommodate the larger cannon. Had they opted for that piece, the design would have had to dispense with the turret and adapt to a fixed casemate-type structure. Space for several machine guns was also anticipated, thus expanding its defensive capacity in close combat. The The model was only partially built, without a turret or mounted armament. In May of 1945, as the conflict was reaching its conclusion, the chassis was sent to the United Kingdom for examination. During the tests, technical obstacles derived from its disproportionate size were identified. The Tiger II had already shown the acceptable limit for vehicles of this type, and the E-100 greatly exceeded those figures. The pressure it exerted on the ground reached 1.43 kilograms per square centimetre, which made it poorly suited for unstable or soft ground. The suspension used, of the Belleville washer type, attempted to distribute this extreme weight. Its dimensions were exceptional: 8.7 meters long, 4.48 meters wide, and 3.32 meters high. Under normal conditions, it would have required a complement of 6 people. Hitler, who had initially promoted the super-heavy tanks as symbols of technical and psychological power, ended up ordering the cancellation of all similar projects in the final stage of the conflict due to resource shortages. This decision completely paralyzed the advance of the E-100, which was left in the hands of barely 3 workers in its last days of assembly. With the collapse of the Third Reich, the model never went into production, nor was it used in combat. Its end was that of an experiment halted halfway, unable to demonstrate whether, beyond the visual impact, it would have been useful on the battlefield. The Panzerkampfwagen E-100 did not manage to fire a single projectile. However, its design continues to be analyzed today as the ultimate attempt by the Nazi regime to create a tank that surpassed all known limits. Despite its short history, it represents an example of how far the German war industry went in its obsession to create gigantic machines, even when their practical utility was already doubtful. Like other projects from that same period, its existence ended up being more symbolic than operational. Page 1000 Rutter, the naval armored vehicle cancelled before rolling. While studies on heavy armoured vehicles advanced, in June of 1942, a larger project known as Landkreuzer P 1000 Ratter was presented. The proposal, promoted by the Krupp Company, contemplated an armoured vehicle with characteristics never before explored in the terrestrial domain. With an estimated weight of 1,000 tons, the design proposed an artillery platform with massive offensive capacity and a crew comparable to a naval complement. According to the blueprints, its length would have exceeded 39 meters, with a width of almost 14 and a height that was around 11. The minimum number of people on board would have been 40. The planned armor for this colossus varied between 150 and 360 millimeters, with an arrangement that imitated the structural resistance of a warship. Regarding its main armament, the plan was to install 2 large-caliber naval guns, the same ones mounted on heavy cruisers. To this would be added 2 other turrets, similar to those of the Maus tank, equipped with 128mm cannons and 75mm coaxial guns. The assembly was completed with secondary armament, anti-aircraft guns mounted in groups of 4, and lighter armament to protect the sides. To move such a structure, 2 possible propulsion systems were evaluated. One of the options was to use 2 engines originally designed for submarines, with a total power that could reach 17,000 horsepower. The other option was even more ambitious, to combine 8 engines from fast boats, which would generate a total power of about 16,000 horsepower. With that capacity, it was estimated that the vehicle could reach a speed of 40 kilometers per hour under the best conditions. However, everything remained on paper. No real tests were conducted, nor was any complete system built in operation. Mobility depended on 6 tracks, 3 on each side, with an individual width of 3.5 meters. This arrangement sought to distribute the weight to prevent sinking on soft surfaces. However, the total weight made its passage on standard roads unfeasible. The pressure on the ground greatly exceeded the tolerance of any unreinforced roadway. Furthermore, crossing conventional bridges was ruled out, and its transport would have required specific infrastructure. Autonomy was also uncertain, since the fuel consumption of this platform far exceeded normal parameters for combat vehicles. A ground clearance of 2 meters and 10 centimeters was contemplated, allowing the crossing of shallow bodies of water. The installation of an air intake was also planned to keep the engine operational in partial wading conditions. This configuration reinforced the idea of a vehicle with prolonged static capabilities. Inside, BMW R12 motorcycles were planned for reconnaissance tasks, especially useful once the vehicle reached its final combat position. Its total volume made it visible from considerable distances, which exposed it to air attacks. Despite having anti-aircraft armament, its size would have made defense against high-altitude bombings difficult. The relationship between the profile and its potential speed raised doubts about its viability as a maneuver weapon. The idea of deploying it in open areas required a complex logistical system, in addition to specific routes and personnel trained for preventive maintenance tasks. The program was cancelled in 1943 by a decision of Minister Albert Speer. Production difficulties, the expense of materials and technical complexity made it unfeasible to continue with the development. The existing facilities could not be adapted to the assembly requirements or the transport methods. Although some elements were contemplated in theoretical models, the construction of physical prototypes or functional sections has not been documented. The project did not advance beyond the blueprints and simulations. The use of marine engines in a vehicle with these characteristics reflected a growing trend in the armaments industry of the time, transferring solutions from other domains without practical validation. While some nations sought to optimize the production of medium and versatile vehicles, this proposal bet on an unprecedented scale, with a focus centered on the deployment of large-scale power. The operational limitations, energy consumption, and logistical requirements placed it outside the functional margins of a realistic war environment. The name Ratte, which means rat, contrasted with its actual size. Although it never materialized as a functional machine, its existence in official documents has made it an extreme example of German studies of the era. Its mention persists in technical analyses, military literature, and fictional representations. In terms of tactical viability, there were no environments where it could perform effectively without being exposed. The time required to prepare its deployment and the technical effort involved turned it into an idea as disproportionate as it was impracticable. Available records indicate that its development coexisted with other ambitious armor projects. However, its magnitude, consumption and demands exceeded the capabilities of the German logistical system toward the end of the war. Priorities ended up focusing on more realistic models within industrial limitations. Thus, the Landkreuzer P-1000 Ratte remained as one of the most representative proposals of technological extremism in 20th century land armaments. Uranium Project, the lost nuclear race of the Third Reich. In December of 1938, two German chemists discovered that uranium, when bombarded with neutrons, produced barium. That reaction was understood by Lise Meitner and her nephew Otto Frisch, who recognized the process as nuclear fission. Frisch verified it on his own weeks later. In Germany, the news circulated rapidly among academics and military officials, who began to glimpse its possible use as an energy source and a war tool. It was then that a group of scientists formed around the idea, later called the Uranverein or Uranium Club. Barely a few months later, in April of 1939, the physicist Paul Hartek and his assistant Wilhelm Groth warned the War Ministry about the enormous military potential that these nuclear reactions could have. At the same time, other academics such as Georg Joos and Wilhelm Handler sent similar reports to the Reich Education Ministry. Shortly after, a small informal team, made up of Joos, Handler, Manfopf and some others, began working in the city of Göttingen. Although they were all very enthusiastic, their investigations were interrupted when they were mobilized with the start of the war in Europe. That was the first, albeit still limited, attempt to explore the use of nuclear energy within the Third Reich. Officially, that group was known by a long and complex technical name in German, but it ended up being eclipsed by the more structured version that would come later. This new effort was simply called the Uranium Project. Under the direct control of the German army, this initiative lasted 6 years with the goal of applying that knowledge to build an atomic weapon. Although it essentially shared the same motivation as the Manhattan Project developed by the United States, its evolution was very different. Unlike the centralized approach of the Allies, the German effort was split among different teams, some with strictly military purposes and others oriented toward energy uses. These branches operated under the supervision of the Reichspost, the postal system which in the Nazi regime also had technological and scientific attributions. The project, despite being state-funded, was never treated as an absolute priority. One of the main technical obstacles was the difficulty in obtaining critical materials, such as heavy water, essential for the reactors. This substance was mainly produced in Norway, at a plant that was a constant target of Allied operations. The facilities were sabotaged several times, and in one of the most well-known episodes, Allied commandos intercepted the last available shipment, preventing its use by the Germans. Meanwhile, the team led by Werner Heisenberg and others attempted to design a functional reactor at various points in the country. One of the best known was in Glocke, an underground structure where an experimental nuclear pile was assembled, made with uranium in the form of metallic cubes. Despite the effort invested, that structure never managed to produce a self-sustaining chain reaction. In parallel, other physicists like Kurt Diebner and Walter Gerlach worked separately on similar lines. The lack of coordination, personal rivalries, and methodological differences weakened the progress. As the war advanced and resources became scarce, the development of the Uran project lost momentum. The priorities of the Nazi high command were focused on other weapons that offered more immediate results, such as the V-2 missiles or the heavy tanks. Although Albert Speer and Hermann Göring were promoters of the project at certain times, the lack of tangible results made their support intermittent. Nuclear fission was complex, expensive, and slow for a regime that was beginning to lose control of the conflict. When Berlin fell in May of 1945, the Allies already knew about the existence of the so-called uranium project. By then, they had already launched Operation Alsos, a mission created to gather information and materials related to the German nuclear program. In that final stage, several renowned scientists such as Otto Hahn, Werner Heisenberg, Walter Gerlach and others were captured and transported to England. There they were housed in a residence known as Farm Hall, where their conversations were secretly recorded in order to discover how much they really knew about the manufacture of nuclear weapons. The Americans, for their part, confiscated large quantities of enriched uranium and other essential materials. Meanwhile, the Soviets were also active. Stalin's Secret Service organized special commandos with direct orders from Lavrenti Beria, with the goal of securing any useful remains of the project and capturing the German experts. General Andrei Drulyov was the one who supervised that operation, which allowed them to obtain several hundred kilos of metallic uranium, tons of oxides, and several liters of heavy water. Additionally, they managed to take very valuable technicians such as Manfred von Ardenne, Peter Thiessen and Ludwig Bevilogua, who were transferred to the Soviet Union with all their scientific knowledge. Despite these late efforts, the balance was clear. The Third Reich failed to develop a single functional nuclear bomb. The combination of improvisation, scarcity, Allied sabotage, and erratic decisions turned the uranium project into a promise that was never fulfilled. Meanwhile, the United States advanced in parallel with clear direction and unlimited resources, culminating in the creation of two real bombs that marked the end of the conflict. The Uranverein remained as an inconclusive episode of what could have been but was not. Torpedo T5, the sound-guided projectile. As the war in the Atlantic became more intense, both sides sought ways to gain an advantage in submarine combat, which developed almost in total darkness. In 1943, Germany surprised by deploying its first torpedo capable of guiding itself by sound. The first experimental model was tested in several submarines, although its testing phase was brief and it did not go into mass production. However, it opened the door to the development of an improved version, known by the crew members as the Zaunkönig. This new torpedo had a revolutionary capability. It detected the noise of enemy ships' engines and propellers and automatically directed itself toward the source of the sound until impact. For the first time, the projectile did not need to be manually guided. It was capable of identifying its target and chasing it by itself, completely changing the logic of combat under the sea. The first major offensive with this new German torpedo occurred in September of 1943 against Allied convoys in the North Atlantic. Its range was around 300 meters, more than enough to impact escort vessels or merchants before they could react. The effect was immediate. The Third Reich submarines no longer fired blindly, but launched a projectile capable of chasing the target and adjusting its trajectory according to the sound it picked up underwater. By that time, the German submarine campaign was suffering increasingly severe losses, partly due to advances in radar, the use of escort aircraft carriers, anti-submarine weapons like the Hedgehog mortars, and increasing aerial coordination from the Bay of Biscay. However, this new type of torpedo briefly returned the advantage to them, forcing the Allies to rethink their naval protection tactics. At the same time, the United States was also advancing with its own guidance technology. At the beginning of that same year, they introduced a torpedo designed to be launched from airplanes, popularly nicknamed the aerial mine, although it was actually much more sophisticated. Its mission was to hunt enemy submarines detected by acoustic sensors dropped into the sea. In May, a Catalina seaplane managed to sink one of the German submarines using this system, although reports differ on which one it was exactly. Later, in June of 1944, an American escort aircraft carrier located a Japanese submarine transporting strategic materials to Europe. The vessel was tracked by 2 torpedo planes and hit by 2 of these acoustic mines, causing it to sink. The impact was so precise that the sound was recorded, and today it is part of the historical archives of the United States. The internal functioning of these torpedoes combined mechanical precision with acoustic interpretation. They incorporated a sensor array that evaluated the environment based on phase differences, generating noise-sensitive directional beams. In more modern models, the patterns could be adjusted digitally, but the initial ones were already sufficient to detect engines, cavitation, or acoustic reflections from the target. In its passive mode, the torpedo picked up the environment without emitting a signal. Once a potential target was detected, it switched to active sonar and began the pursuit. If the target used countermeasures, the system had to decide between false and real signals, guided by the consistency and strength of the sound. Before launching the weapon, the firing platform defined search parameters. These included the estimated depth of the target and the area where it could be detected. Thus, the torpedo already left with an initial orientation before activating its independent detection. This coordination between the launch system and the autonomous guidance caused these devices to be compared to modern fire and forget-type missiles. The appearance of this threat forced the Allies to develop urgent solutions. One of the most used was the Foxer noise generator, a towed decoy that emitted sounds louder than the propellers themselves. By following this noise, the torpedo circled until it ran out of fuel. This strategy was so successful that of the more than 700 German torpedoes launched, only 77 managed to impact. However, using Foxer had a cost. It blocked the ship's own anti-submarine sensors, leaving other submarines undetected. Another Allied tactic was the maneuver known as the step aside. Upon identifying an imminent attack, the ship executed a sharp turn out of the torpedo's acoustic range, managing to evade it and, in many cases, counterattack the responsible submarine. These combined solutions once again reversed the technological advantage, and German submarines were again at an operational disadvantage towards the end of 1944. On the Soviet front, the wreckage of the U-250, sunk in shallow waters, allowed for the recovery of intact German torpedoes. This finding, along with the capture of the U-555 by the United States, offered the Allied powers the opportunity to thoroughly examine the enemy's technology. Although the Soviet Union promised to share technical details with the British Navy, the collaboration was cancelled when the officers arrived in Kronstadt. They were not allowed to see the armament and returned without useful data. After the war, many navies around the world began to incorporate similar systems. As early as the 1960s, the United States Navy developed a decoy known as Nixie. It was a device towed by ships, which emitted acoustic signals designed to confuse sound-guided torpedoes. Instead of heading toward the real vessel, the projectile ended up following this artificial noise. Over time, the system was improved and more advanced versions emerged, such as one that is still used today. However, the logic remains the same: to get the torpedo to deviate by chasing something that sounds louder than the actual target. The acoustic concept remains current in modern torpedoes, although with substantial improvements. The ability to distinguish between different types of signals, even in noisy environments, allows new devices to operate with greater precision. Even so, the basis remains the same as that introduced by the T5, a submarine projectile that listens, decides, and attacks without requiring further guidance. This type of weapon represented a before and after in the history of naval combat. Although the first versions were not entirely effective due to enemy countermeasures, they forced the Allies to change their tactics in the middle of the conflict. Simply by existing, they completely altered the relationship between hunter and prey beneath the sea and left a very clear lesson. In submarine warfare, sound could be as deadly as any explosive. Me-262, the jet fighter that arrived too late for the war. During the last years of the conflict, Germany desperately sought to develop an aircraft that could curb the Allies' air superiority. The result was a machine completely different from anything seen before. In 1944, the Me-262 appeared as the world's first jet fighter to enter combat, and it did so under the codename Schwalbe, or Swallow. This aircraft was not just a technological improvement, its speed greatly surpassed that of any Allied aircraft. While British and American fighters barely reached 700 kilometers per hour, the Me-262 crossed the sky at 900, which made it practically unreachable during direct engagements. It did not need to escape, because no opponent could follow it. Powered by two Jumo 004B jet engines, it could take off and reach its cruising speed in less time than it took enemy bombers to organize their formation. It had a very advanced aerodynamic design with swept wings, retractable landing gear, and a cockpit specially designed to increase visibility. Its slender and elongated fuselage not only made it elegant but also extremely functional. In terms of armament, it was also impossible to ignore. It was equipped with 4 Mk10830mm automatic cannons placed in the front. That firepower was enough to shoot down a heavy bomber with just a few bursts. Some models even incorporated R-4M air-to-air rockets, capable of hitting entire aircraft formations from a safe distance. For the first time, Germany had in its hands an air weapon that was not only revolutionary in theory, but also deadly in practice. Combat reports confirmed its superiority. Units that managed to take off and engage recorded a high number of kills with hardly any losses. In direct confrontations, Allied pilots recognized that they could not match its speed, maneuverability, or offensive capability. During its brief operational time, the Me-262 managed to shoot down more than 500 enemy planes. No other German model of that period achieved such performance with so few units deployed. Despite this, the new aircraft would not arrive in time to change the course of the conflict. Its development had begun years earlier, but it was not until 1944 that its use in combat was authorized. By then, the conditions were very different. The Luftwaffe was in retreat, short of trained pilots, and with air bases under constant threat of bombing. Fuel was limited, and workshops could not maintain constant production due to Allied attacks. Hitler's own decision negatively affected the aircraft's deployment. For a time, he insisted that it be adapted as a ground attack aircraft instead of being used only as a fighter, which further delayed its entry into service. By the time its use as a pure interceptor was authorized, it was already too late. Factories were being attacked, resources were scarce, and experienced pilots were in short supply. Many of those who flew the Me-262 did so without having received sufficient training to handle an aircraft of those characteristics. In total, around 1,400 units were built, but only a fraction actually came to operate in combat. The constant attacks on airfields, the lack of spare parts, and the critical state of German industry meant that many jets could never take off. Those that did often did not find suitable conditions for landing and ended up damaged or destroyed in forced maneuvers. The Me-262 was, without a doubt, a technical marvel ahead of its time. It represented the future of combat aviation and demonstrated in a few months what would have been possible had it been developed years earlier. Its ability to outperform any Allied fighter, its devastating armament, and its revolutionary design made it a real threat on paper and in the air. But war is not won with prototypes, and by 1945 it was already evident that the Allied advantage in numbers, logistics, and control of the sky could not be reversed with a single innovation. Although the Schwalbe II was living proof of German technological ingenuity, it also symbolized the collapse of a war machine that could no longer sustain its own advances. The jet, invulnerable to enemy fighters, had arrived, but it did so too late to change history. The Seeteufel amphibious submarine, the elephant that would never sail. In the middle of 1944, when the war was definitely turning against the Third Reich, the Kriegsmarine decided to bet on unusual technical solutions. One of those bets was the development of the Seeteufel, a midget submarine conceived to operate with amphibious capabilities, capable of moving on land and submerging without external assistance. The concept emerged at the Torpedo Testing Center in Eckernförde, where a team led by Alois Lödiger took barely 4 months to convert a blueprint into an operational prototype. The most notable particularity of the Seeteufel was its double nature. It not only had to sail underwater like any submersible, but also move on land thanks to its tracks installed on both sides of the hull. This feature allowed it to be deployed from a standard 35-ton armoured trailer without relying on cranes, cargo ships, or port infrastructure. Such mobility offered combat units great flexibility to select launch points in remote or difficult-to-access areas. It was also considered useful for missions where operational discretion was key, since the vehicle could move by land to an isolated coast, enter the water and continue under the sea without visible intervention. With a length of 13.5 meters and a width of barely 2 meters, the Seeteufel displaced 20 tons in operational conditions. Its construction was optimized to achieve maneuverability and stability while submerged. Tests carried out by Combat Unit Test Command 456 revealed that the submersible reached an operational depth of 21 meters, falling slightly below the 25-meter limit envisioned in its design. Despite this, the descent and ascent maneuvers were performed with notable smoothness, assisted by a quick-response depth rudder and an aircraft-like joystick control system. Among its technical advances was a plexiglass breakwater that improved pilot visibility during surface movement. It also included a magnetic compass mounted on the snorkel mast, which could be read indirectly through mirrors arranged in the command center. This arrangement prevented the operator from having to expose his position or abandon control to check navigation. In terms of armament, the Seeteufel was designed to use 2 G7 torpedoes of 53 centimeters caliber. Unlike other midget submarines, this design could launch torpedoes at full distance, thanks to a sub-propulsion cell system that compensated for their initial impulse, allowing them to reach ranges of between 1 and 12 kilometers, depending on the type of torpedo used. Alternatively, the submarine could carry 4 sea mines distributed along its fuselage. As a means of short-range defense, it was equipped with a machine gun or a flamethrower, intended for surface combat situations or during land movement. However, the project faced critical limitations from its initial stages. The planned engine, a 200-horsepower diesel combined with a 100-horsepower electric propeller, never materialized. Instead, the prototype was equipped with a diesel engine of barely 80 horsepower and an electric one of 24, a combination clearly insufficient for the design requirements. This power deficit compromised both submerged speed and effectiveness in land movement. In real tests, the Seeteufel reached a maximum of 8 knots underwater and 10 on the surface. Another weak point was its tracks. Being too narrow, they increased pressure on the ground and caused the submarine to easily sink in sandy or muddy areas at the edge of the sea. This situation could severely slow down progress or even generate a risk of running aground. Redesigning the traction system with wider tracks was proposed, but the tests were unable to implement them before the end of the conflict. Furthermore, the weight of the vehicle, which earned it the nickname Elephant among its operators, made any attempt to lighten it difficult without compromising its structure. Serial manufacturing was to be carried out at the Vogle plant, located in Bremen, where 3 units were started, and at least 20 more with improved propulsion systems were planned. None of these units were finalized. Towards the last days of the conflict, the only operational model was transported to Schlüttup, on the outskirts of Lübeck, and eliminated by direct order of the Naval Command. The area designated for its protection and testing received the code name Blaukoppel. Despite its defects, the Seeteufel aroused interest for its potential capabilities. Future variants equipped with wire-guided torpedoes, such as the grill type, were under development, as well as specific adaptations for dive attacks against coastal targets. None of these proposals went beyond paper. The failure of the Seeteufel was not due to a lack of innovation, but to a combination of technical problems, insufficient materials, and the urgency of the wartime context. Even so, it left a record of a serious attempt by German military engineering to combine land mobility with submarine attack. In technical archives after the war, the project was reviewed by various powers as an example of hybrid design, although it was never operationally resumed. Thus, the Seeteufel ended up as a technological anomaly of the Second World War. Born too late and with too many shortcomings to influence the development of the conflict, it was one more of the desperate experiments of the Third Reich to gain time against the imminent collapse. Although it never entered combat or surpassed the prototype phase, its amphibious design, its complete armament system, and its operational autonomy place it among the strangest and most ambitious projects of the Nazi arsenal, forgotten amidst the chaos of the last months of the conflict. Arado E.555, the flying wing that targeted New York. In late 1943, Arado engineers began sketching an aircraft capable of crossing the Atlantic and reaching United States territory. The proposal, conceived at the Landeshut facilities in Silesia, started from a simple premise: to develop a machine fast, light, and powerful enough to bypass Allied air defense. Under the technical direction of Dr. Lauter, the German team began exploring flying wing variants with a design that eliminated unnecessary surfaces to reduce air resistance. In April 1944, the minimum requirements were formalized: high speed, a range exceeding 5,000 kilometers, and the capacity to carry at least 4 tons of bombs. Discussions focused on finding the most viable way to achieve that combination. In a few months, more than a dozen proposals were presented. All followed the same basic principle: a 2-seater, long-range, high-speed bomber powered by jets. Some ideas even considered including up to 8 engines. Despite the engineers' enthusiasm, none of those designs passed the conceptual stage. The main model, designated as E.555-1, was the most developed of the group. It was a fully metallic structure, manufactured with a combination of steel and duralumin. The fuselage was minimal, as the plane followed the logic of a pure flying wing. The pressurized cockpit occupied the front, with a circular section that smoothly integrated into the aerodynamic profile. On the sides, 2 vertical stabilizers provided directional stability. They were located more than 6 meters from the center of gravity to ensure effective control. The landing gear consisted of 2 tandem systems with double wheels that retracted into the wings. In the front, a double wheel located under the cockpit retracted in the opposite direction. As an alternative for overweight conditions, the use of a disposable auxiliary landing system was envisioned. 6 BMW 003A jet engines would be installed on the top of the wing, aligned in parallel. Subsequently, the possibility of replacing them with 6 Heinkel HES-011 engines, which offered greater thrust, was raised. This reconfiguration would allow for higher speeds without compromising the structural integrity of the aircraft. Every technical decision pointed to a single objective: to create a bomber that could reach cities like New York or Chicago without refueling. The defense of the aircraft was also carefully planned. 2 30mm Mk-103 cannons would be located just behind the cockpit, mounted on the back of the fuselage. A remotely operated turret with 2 MG-15-120 cannons would be installed behind the pressurized command section. Another pair of cannons of the same type would be placed in the rear, controlled via a periscope from an armored weapons station. As the blueprints and calculations accumulated, the Luftwaffe's priorities began to change. In December 1944, the Reich Air Ministry ordered the cancellation of the program. The war was in a critical phase, with resource shortages, loss of territories, and an Allied air offensive that punished German factories daily. Production had to focus on defensive fighters and proven models. The Arado E.555 thus passed into the archive of unfinished projects. Of all the proposed designs, one stood out above the rest. The E.555-6 model, with a wingspan of more than 28 meters, was intended to incorporate 3 BMW 018 engines, which were not yet fully developed. With auxiliary tanks, it was calculated that it could cover up to 7,500 kilometers. Its profile responded directly to the initial demands of the project: cross oceans, attack strategic targets, and return without stopping. Today, this projected bomber retains a certain appeal among technical modeling enthusiasts. The Revell company produces a 1/72 scale replica based on its original blueprints, which some fans reconstruct using speculative camouflage patterns. In that field, the E.555 ceased to be a threat over the Atlantic to become an exhibit piece. Its designs are part of the historical catalogues of advanced aviation of the Third Reich, as one of the few members of the America bomber program with detailed technical documentation. The ideas surrounding the E.555, along with other designs such as the Horten Ho 229 or the Junkers Ju Tu-187, show a clear trend in the last years of the conflict, replacing conventional combat with experimental technology. Germany was no longer trying to win the war on the fronts, but to imagine a blow that would change the rules. The E.555 was one of those imagined blows. Reichenberg, the manned bomb of the Leonidas Squadron. After years of war and with the front collapsing, Nazi Germany attempted to convert its last resources into desperate weapons. One such attempt was the Fliegerfaust Fe-103 Reichenberg, an adapted version of the V-1 flying bomb, equipped with a cockpit for a pilot. This apparatus was designed as a manned projectile within the program of the special Leonidas Squadron under the command of Kampfgeschwader 200, a covert operations unit of the Luftwaffe. The idea stemmed from a concrete need to strike Allied positions with precision, especially ships, using a basic yet lethal machine. From the beginning, two viable platforms were evaluated: the Me 328 fighter, which had serious technical flaws, and a modified version of the V-1, finally chosen for its structural simplicity. This project was spearheaded by Otto Skorzeny, who had the collaboration of test pilot Hannah Reich. She had promoted the use of single-person aircraft for suicide missions since 1943, an idea that took shape when it was picked up by the High Command. The program was named Reichenberg, taken from a town in the Sudetenland where the original proposal was formulated. Aspirants to pilot these devices accepted the conditions of a mission with no guaranteed return, knowing that the operation involved extreme risk from the start. The training process was developed under strict protocols and without access to sufficient means. In the middle of 1944, the German Institute for Gliding Research, located in Enrich, took on the construction of the prototypes. In parallel, an assembly line was set up in Dannenberg, where the V-1 bombs were transformed into versions with a cockpit. The main modifications consisted of the incorporation of an ejection seat, control stick, and adequate frontal vision for the pilot. The cockpit, located in the forward part of the fuselage, was metallic and enclosed, with basic instrumentation. The propulsion remained an Argus AS-014 pulse jet mounted on the fuselage. The wings, straight and non-folding, maintained the design of the original V-1. The landing gear consisted of fixed skids instead of wheels. Takeoff was carried out with the help of a Heinkel He 111 bomber, which carried the Reichenberg attached under the right wing. Once released, the pilot had total control of the apparatus until impact. In October 1944, 4 distinct versions of the apparatus were officially established. The first was a motorless glider, intended for training pilots to become familiar with the controls. The second had a double cockpit and was used for advanced training. The third completely replicated the shape and controls of the definitive model, although it still lacked active propulsion. And finally, the fourth version already incorporated the functional engine and was directly intended for real missions against enemy targets. Although the operation of the Reichenberg implied extremely high risk, the engineers asserted that a possibility of escape existed. The ejection seat, along with the armored cockpit, offered a last option for survival before impact. However, in practice, the decision times were so brief that few trusted the system's effectiveness. The test flights were supervised by Hannah Reich, who also flew in some of the models. During one of these tests, the apparatus became unstable, forcing an emergency evacuation. Although the pilot survived, the episode showed the design's limitations and provoked internal debates about the system's tactical viability. The program had a dozen pilots in training and several operational prototypes. However, Germany's military situation was rapidly deteriorating. Production priorities focused on defensive models like the Messerschmitt Me 262, and the Reichenberg was relegated. In November 1944, the program was suspended by direct order of Hitler, who considered that the moral impact of the suicide missions could be counterproductive for public opinion. Despite having been conceived for combat, no Reichenberg was used in real missions. The project remained as one of the many desperate attempts by Nazi Germany to reverse its defeat through extreme solutions. When the war ended, the prototypes were confiscated by Allied forces. Some units reached museums or were subjected to analysis for their unique characteristics. From a technical point of view, the Fe-103 Reichenberg represented a rudimentary adaptation of existing technology. It lacked real innovation, but its development reflected the High Command's desperation to find quick and economical ways to attack the enemy. The use of volunteers willing to pilot explosive projectiles marked an ethical limit within the conflict. Although its application was avoided, the concept was studied by other countries after the war. Nazi sonic cannon, the acoustic prototype that damaged with vibrations. Long before the war began, it was already known that extreme vibrations existed that the ear could or could not capture, some too high-pitched, others so low that they were only felt. In Germany, several scientists decided to test how those waves affected real people. They used prisoners to experiment with very low and very high sounds. They discovered that the lowest ones caused complete disorientation. They caused stomach pain, dizziness, vomiting, diarrhea, and shortness of breath. They also altered the mind. Intense fears emerged without explanation. Some tried to harm themselves or lost their minds. It seemed that they had found an ideal weapon, but taking the experiment to open spaces was a failure. There was no way for those waves to travel only toward the enemy. The same personnel operating the machine also suffered the effects. Furthermore, the apparatus was huge and barely worked at short distances. The commands concluded that it was better to stick with the usual machine guns. Given the failure with low waves, German researchers changed their focus. They began to look for other ways to use sound as an attack tool. One of them was Richard Wallerschek from the Institute of Acoustics in Tyrol. He directed the creation of an apparatus that could cause fainting or even kill by just emitting a loud noise. The artifact was ready in 1944. In the center of a large circular reflector more than 3 meters wide, they placed a tube with an ignition system into which methane and oxygen were injected. By igniting that mixture again and again, controlled explosions were generated that produced a continuous hum with the desired frequency. At less than 60 meters, the impact was such that many fell unconscious in seconds or lost their lives. But time was running out. In January 1945, the authorities suspended the funds. They said that, given the situation on the front, the use of sound waves made no practical sense. When American troops captured the location, they found the apparatus. A secret bulletin from May 1946 described it, at less than 60 meters, the force of the sound is enough to kill. However, they also stated that due to its limited range, the weapon was useless in real combat. That sonic prototype was just one of many. In the end, the Third Reich left behind a graveyard of unfinished ideas, forgotten blueprints, and weapons that never managed to change the course of the war. Most never left the drawing board. Others failed due to lack of time, technology, or tactical logic. What remained were rusted pieces, disconnected rumors, and documents marked as top secret today. Those remains only serve as a reminder of how far an ideology can go when it tries to convert science into mass destruction. They were machines designed to terrify, but fear was not enough to win the war.